busy schedules for all of us. So I appreciate your engagement today, appreciate your questions, appreciate your comments. I'm stepping in here as a sort of one-time lead instructor. So I appreciate we haven't had the chance to work together. So please, as I make progress during the lecture, do let me know if I'm going too fast. I don't think there would be a problem with going too slow because we have a lot of ground to cover. But definitely, if I'm going too fast, let me know. Before we begin, I want you to keep something in mind for today. We will cover a lot of code today. We will cover exercises today. And I want you to focus on the big picture. I don't want you to look at the code and trying to figure out, hey, why is there a dot here? Why is there this function there? I'm going to talk about the main libraries and what they do, but getting into the code as we're running it, focus on the big picture. I'm telling you this right now because if you haven't looked at the lecture materials, it's possible that some of you might get a little bit overwhelmed. There's a lot of code there. But again, just as a disclaimer, focus on the big picture, focus on the problem we're trying to solve as opposed to the code itself. The code itself, you'll be able to go back and reference, and you'll be able to run it over and over again. The code is actually very well documented, so you'll see what almost like each block of the code, what it does. And of course, if you have questions, you can ask me or you can ask your TAs. But the point of today's lecture is to solve the real world problem. As with any class, here is to solve the problem. And I want you to focus on that. Okay. So just a bit of a disclaimer. Before we begin. Today's lecture will be about supervised and unsupervised machine learning. So it's the first time that we'll be touching these two types of machine learning. And it's the first time that we'll be talking about the use cases in the real world of the applications of supervised and unsupervised machine learning. So let me go ahead and share my screen. Hopefully it's visible.
Yep, perfect. We can see it.
Perfect. Thank you. And let's dive right in. What is the learning objective today? The learning objective is to learn about supervised and unsupervised machine learning models. We have two blocks today. One talks about the supervised and the other one talks about unsupervised. So let's start with the supervised. What is the supervised? What does this even mean? Supervised versus unsupervised. You may have heard these words before if you don't know what they mean. In very simple terms, supervised machine learning model means that you have the ground truth. You know what the real world looks like, and you're trying to predict the future using that ground truth, or you're trying to predict something using the ground truth. For example, let's say you want to predict people's income. You have your customers and they're purchasing something, and you're trying to predict how much they earn based on how much they buy, for example. And the idea is that you have your real world data and you know the characteristics of your buyers, and you also know their incomes. So you're using their incomes as a ground truth to train the model on, so that once you have a new set of people with the purchasing behavior, you can use your model to predict what that set of buyers' income is. Okay, but the idea is that you have that ground truth to begin with, and that's what you use. Now, in unsupervised machine learning, we don't have that ground truth. So we actually don't know or we're not, our goal is not to predict anything necessarily. Oftentimes, our goal is to, for example, explore or to group certain things. So, for example, today we'll talk about market basket analysis. And what that is trying to figure out what items are purchased most frequently, for example, in the shopping carts of your customers. So you know what they buy, but you don't know, there is no ground truth. There's no ground truth to be had to begin with, because there's no right amount or variety of purchases that people make, right? So people make purchase whatever purchases they want. And so your goal is just to explore what are those most popular combinations, as opposed to try and predict what the next customer is going to purchase, right? So, and it's not that one supervised is better than unsupervised or vice versa. It's just truly, genuinely different methods for different problems at hand. We will start with the supervised machine learning. And there are two major types of supervised machine learnings that are known in statistics: regression and classification. In the most sort of fundamental ways, the difference between regression and classification is in what you're trying to model. Regressions usually deal with numeric and continuous data that you're trying to predict. So, for example, if you're trying to predict income, that would most likely be some kind of regression, because income tends to be a continuous type of data, continuous variable. You go from 0 to some high number of in income, but that is a continuous number. Whereas the classification usually is used for categorical variable. Recall some time ago you were looking at different types of data. So categories is something that the classifications are concerned with. So for example, let's say you're trying to predict if something is someone is going to be approved for a loan, right? We have today this case study. So it's the ground truth here is that someone is either approved for a loan or not approved for a loan. So that's two categories you have. Sometimes you have more categories where, let's say, you're trying to predict where, in which region your buyer is going to be located. So let's say you have 4 regions, and that also will be a classification problem because you're dealing with 4 categories. Okay, so at the very sort of fundamental level, regression, numeric, classification, categorical. Moving on. I am going to first go through the theory, and then we'll start diving right into the practical example together. Let's dive a little bit more into the regression model. The most common type of the regression model is linear regression. Now, what is a linear regression? Linear regression is our attempt to draw a line. So I'll try to show you an example. To draw a straight line that will capture the essence of our data. So what do I mean by that? Imagine you have different observations in your data. You have, let's say, let's take a simple example. Let's say you're trying to predict someone's weight based on their height. So your model would look something like this. Your weight is something you're trying to predict. Then there is some number, some variable that is sort of not captured by what your independent variable is, and then you have the actual variable that you think is going to affect your weight, which is height. So the idea is that you have a lot of observations, and those observations are lying somewhere on this chart. So you have someone, I don't have a scale here, but let's say you have someone with low height and low weight. You have someone with a high weight and high height, and then you have people in the middle with higher weight and lower height, and vice versa. The reality when you try to model is that you will never find a way to model um, or create a model that captures every single of this point, right? So there is no function in mathematics that would sort of like cut across all these different data points. And quite frankly, it's not the point of the modeling. The point of the modeling is to capture the essence and general essence of your what's going on with your observations. And when you see something like this, you could imagine that you could draw a straight line that says, hey, I know that I'm not capturing all the observations, but this line captures the majority of these observations. So these observations are lying somewhere very close to this line. And so I am able to then predict or use this function to predict my next observation. And so in this case, for example, if you have someone with the higher weight, you could say, based on this function, I can predict at any point in this line, I can predict, for example, here, what the height is going to be. Of course, you might ask a question, well, but what about all these inaccuracies, right? So for example, here, I have the real values here. So the person with this weight and this height is over here, but the predicted value is here. So isn't there an inaccuracy? And the answer is absolutely. Every model comes with inaccuracies, which are called errors. And in this particular case, we're talking about the error definition, and the error definition is the delta between your predicted value and your real value. Okay, so that's important to know. A couple things that also are important to know before we dive into the real example is there are ways to optimize these errors. Of course, in general, you want to keep this line as close to all observations as possible. But the world is not perfect, so is not all the statistical models. And because of that, there are ways you can optimize. There are two ways you can optimize models. Generally speaking, there is something called loss function, right? So loss function is essentially your real value minus your predicted value. You're trying to minimize that. And there are different ways of doing that, which I'm not going to get into in detail, but there are different error types that you can report. And then, of course, there is a cost function that you can also calculate. These methods are used to essentially do two things. First is optimize the model and make sure that it represents the real world as close to it as possible. And secondly, it allows you to report the level of confidence you have in the model so that even if your model is not 100% accurate, that people you're reporting it to, they understand what the loss function is, what the cost function is, and they can make their own the conclusions. Okay, so this is theory. What I would like to spend most time on today is the actual examples, because I think this is going to bring it to life for you. And so again, just make sure you focus on the big picture, okay? And of course, any questions you have, I'm going to be making pauses after each example, after each case study, and we can talk about your questions. One more thing I'm going to say before we dive into the case study is I'm going to actually spend more time on the first case study than the second, because there is going to be some level of overlap between the first and the second within the supervised examples. And I will go a little bit slower, but then, of course, the same steps that will appear in the second example, I will go faster with them. So the first one we'll spend more time on. Let's start with the linear regression model. Let's look at our case study, first of all. Imagine that you are a data scientist within an insurance company, and the insurance company has records on their customers, And the records include the following information. So they have age, sex, BMI of the customers, how many children they have, whether they're a smoker or not, which region they live in. And finally, the most important, the charges, the amount of charges that the insurance company covers for each customer. And as any insurance company, what your job as the business owner is to minimize the charges, or at least be able to predict the charges based on the characteristics of your customers. Now, you are a data scientist, and your job now is to build a machine learning model that helps predict the number of charges imposed on the company for each new arriving customer. So when the customer comes in, you measure all these things on the customer, and then you're trying to figure out what would be the charges so that the company can do two things. A, calculate the premium correctly, and B, plan their financials better for the future, or essentially do a better forecast. Let's start with importing some libraries. So what are the libraries in Python? And you may have covered this in previous classes. Libraries are the important components of Python language, because they allow you to utilize all the knowledge and all the programming that other programmers have put in before you to make your life easier. So, for example, if you take back, like, let's say, I don't know, 25 years ago, the programmers and even statisticians, they had to code a lot of things from scratch. So literally program, even the statistical models had to be programmed from almost nothing. In this day and age, especially in Python, we have sort of pre-packed or pre-packaged models. We no longer have to program a linear regression ourselves. We just have to call on it from the library, and then that regression becomes available to you and you can run it. These libraries have made a lot of data scientist jobs much easier, saves time for a lot of people, and really moves us into this world of having a sort of like a Lego type architecture with programming, where all you need to do is put together building blocks in your machine learning pipeline, and then you're able to run it a lot more efficiently than in the past. So these libraries are here, and I'm not going to get through, or maybe I'll just quickly go through them just to orient yourself. The first library is called scikit-learn. So the scikit-learn is one of the most common libraries in machine learning in Python. It has lots of different models. In fact, I highly recommend that you remember it and you use it. It's probably, if not the most popular, but definitely one of the 3 most popular libraries for machine learning. Then there's pre-processing. So pre-processing is the module where you can pre-process your data. Then, of course, there's label encoder. So label encoder allows you to turn your categorical features into numerical labels. Not that you're trying to change the data itself, but sometimes it's easier for Python to process your variables if they are encoded in numerical terms. Then there is model selection. So model selection is a module within scikit-learn, and it allows you to evaluate models, different models, and compare them. Train test split is a function within that module, and it allows you to split your data. We'll talk a little bit more about this later. Why do you even need to split your data? Linear model is also a module that runs both classification and regression tasks, so definitely a very important component. Linear regression is the linear regression model itself. So that's what I meant when I said before programmers had to program regressions. Now you don't have to. You just call on linear regression, specify your parameters, and then voila, you have the output. Metrics is a module also specifically designed to evaluate the performance of the machine learning model. And then there are different errors that you can estimate to understand what is that, what we talked about, the loss function, the cost function, how accurate your model is. I'm just scanning through the chat. Okay, I think we're good so far. Let's import those functions. So you see this piece of code. It basically what it does, it imports all those modules that we just talked about. I'm going to go ahead and run them. You won't see any output because all you're doing is you're importing your data. By the way, if you want to know what data or where that data is located, you go to the left side over here, and then if you click on the drop down here on the data side, this is the insurance file that you'll see over here. So it's already preloaded for you. And that's what we're going to do. We're going to load the data now because Python Notebook doesn't have it yet. So make sure that over here in line 26, you click run so that you can load your data from the data folder. Again, you'll see nothing yet just because all you did was you created DF, stands for data frame. You just created a data frame that contains your insurance table. Data frame is a very common concept in machine learning and data science in general. It's a construct that you use basically in a tabular format that you use to run a lot of your pre-processing, post-processing, and actual modeling. Let's start with exploring the data. So the head function here would help us do that. If you run the head of the data frame, essentially what it does, it gives you the first few records to look at. It's not meant to for you to do anything meaningful with the data. It's just a preview. So you can see that we have 0, 1, 2. So these are our records. We have age, sex, BMI, children, smoker, region, and charges in dollars. Can I say just data instead of DF? It's a variable after all. So yeah, it doesn't matter how you call it. You can call it data. My point is here, you have to load your data into a data frame and you give it a name. So DF happens to be the name of the data frame. The naming is important in Python. If you loaded the data into data frame called, I don't know, monkey, then you can't use DF anymore. You have to call it monkey. So just make sure you are consistent with the naming convention within Python. Moving on, let's look at the shape of our data. So there is this function called shape, and what it does essentially, it looks at it can tell you how many rows and columns the data set has. So I'm going to go ahead and run this. You'll see here it says print. If we didn't have this, it would just give us 2 numbers and it wouldn't be very legible. And so because of that, we just created a more user-friendly output using the words there are rows and number of columns. But this is where the data comes from. The number of rows and the number of columns come from here. We also want to understand how many missing values we have in the data. This is very important before you do any kind of pre-processing on the data, because if you end up having a lot of missing values, then you need to seriously think about how to handle them. And in fact, one of the exercises today, in one of the exercises, we'll be doing that. So info allows you to do just that. So I'm going to run info on our data frame. And you see that even though we have 1,338 entries or rows, it basically what it does, it breaks them down with the count of the non-null values. Non-null means that they're non-missing. And you see that the majority of our data doesn't have null values except for this one. This one has 3 missing values. Now, and you'll see it also here if you run so this way, it's not the most efficient way to check for null values. There is a different way. It's called isNull and then sum. So what you do is you run the isNull function and then you sum the records that are null. And if you run that, you'll see that the same thing, you're going to see that BMI has 3 null values. What you also might want to do, and we'll deal with these 3 later, but the other thing you want to do is you want to understand the statistical shape of your data. What do I mean by that? In your table, you have a lot of numerical variables, right? You have age, BMI, children, number of children, and charges. And sometimes it's very pertinent for data scientists before they do any kind of modeling is to understand the generic properties of your data. So in this case, I want to not just know how many records I have, but I want to understand their mean, standard deviation, min, max, and also some ranges, right? The 25%, the bottom 25%, 70, the top 25%, what type of values they have. This gives you some knowledge of the data distribution. And in linear regression, distribution is important. So let's go ahead and run this. You're going to see the output over here, and it allows you to explore it for your exploratory analysis. The question, how serious are null values when using machine learning to calculate things? Do you have to get rid of the whole row where there is a missing column value? Good question. It depends. The answer is it depends. So in our case, we will be deleting them. But in general, if you will be deleting them because 3 rows are not that big of a deal in our case. But there are some cases where you can't do that. You have to replace them with something else. And usually, I'm skipping ahead a little bit, but usually if you have to replace your data with something or missing data with something, you typically replace it with either mean, the average, or mode. Mode is the most commonly seen data within your variable. And the reason why you have to do that is because sometimes the amount of missing data is so much that it becomes impractical to run the model by deleting all your missing values. And so this was the numerical shape of your numerical variables, but remember, also categorical variables that we have. We have sex, which is female or male. We have smoker status, yes or no, and we have a region, and there are 4 regions there. So for you to run the describe function here, you'll just need to include object. What it does, it automatically selects only categorical variables and runs the describe function on them. And you see the same thing. You see the counts, you see how many unique values are in each category. You see the top one, right? So just an example, if you have only 2, then it's easy to deduce the second one. In this case, it's not so easy, but I'll show you later how to do kind of like a better way of looking at different categories. And then the frequency, how often this value appears. And you see the total count here, right? So even visually, you could tell that the majority of people in your data set are female, for example. And here, the majority of people do not smoke. And here, probably like a fourth of the people live in Southeast, which makes sense. So which means that your data is fairly well geographically distributed. Um, so Troy is making a really good point. The data set for my project started with like 70K rows, but after getting rid of nulls, it's about 6K. Yeah, so this is a problem for sure. If you end up with a data set like that, you should not, I mean, I don't know your situation, but just on the face of it, I definitely do not recommend getting rid of null values. So in that case, you'll have to backfill probably. Um, we can also check the number of unique values in each column using m unique. So this is what I was talking about before, right? So you can run the m unique function over here, and it tells you, how many unique values you have. It's not super practical for numeric variables, because in the numeric variables, like here in age, for example, you have 47 unique ages in your data set. Well, how practical is that? I don't know, right? Like somebody has, 16 years, maybe appeared 3 times, and 17 appeared some other number of times. But it is very relevant for the categorical variables. So for example, sex or region. Okay, any questions so far? I want to move on to cleaning data. So let's look at cleaning our data. Let's look at cleaning our data. We need to remove missing values. We just talked about the fact that we only have 3 missing values. It's not going to affect our predictions or our model outcome. So in this particular case, let's drop them. So we're going to use drop NA function to drop. And then in the second step, we'll just do the final check to make sure that our final data set doesn't have missing values. So I'm going to go ahead, run this, and then you see in the output, in fact, every field has 0 missing value. What about unknown values? Do unknown values also count as null values? Great question. If within the field you have the value unknown, so it's actually written there unknown, it doesn't treat it as a missing value. To truly have missing value, you should not have anything there. We'll see in one of our examples today that in some cases we will have NaN abbreviation as a value. In that case, Python will not recognize it as a missing value. So we cleaned the data, we pre-processed the data, we looked at it. Let's move into visualization. So we need to figure out first, let's run some distributions of your data and try and figure out how normally it's distributed. The function that we will use here is called matplotlib. It's a very common function in Python. It's used for all kinds of histograms, distribution charts and things like that. And it's very useful because what it does, it essentially allows you to quickly create distribution charts with the data that's continuous. So in this case, for example, take a look at the age distribution. We have frequency as y-axis and age as the x-axis. So what matplotlib, or what the histogram in this case does, it created bins automatically for us from the age field, and it created the distribution chart. So we see that the majority of people kind of fall in probably like under 22, or at least that's the biggest category, but then you have a long tail of people with different types of age groups. The next one would be a pie chart. So in the pie chart, we want to look at the region distribution. So recall that when we looked at the frequencies, we saw that I tried to kind of do the mental math. And I said, hey, about the fourth of your customers lived in Southeast. Well, there is a kind of more structured way of checking that. So you can run a pie chart. And in the pie chart, you see that it's fairly well distributed. You have kind of 25/26.7% of your data sits in one region. And so you can conclude from here is that your data is well represented. The reason why representation is important is notice how we only have about 1,300 records, right? 1,300 records in real world is not common, right? In this day and age, usually you would deal with hundreds of thousands, if not millions of records. And especially in Amazon, you're dealing with potentially hundreds of millions of records, depending on what you're trying to do. And of course, any machine learning or any kind of processing in Python takes time. So it's impractical for you to do every single analysis on hundreds of millions of records. It's going to take you a long time. What if you make a mistake? So it's common for data scientists to take a sample of the data to run your models on. And then once you validate your models, you can run them on a bigger sample. But what's sometimes happens with sampling of the data, by sampling the data, you're running a risk of introducing bias. And so running these types of distribution charts are important because you essentially get an idea of how close is your sample to the general population that you have in your real data. So I mean, here, I don't know. So maybe in this particular insurance company, you tend to have younger people. And I'm not an expert, but here I can tell with a high degree of confidence that the sample is at least well distributed geographically. Because if it's a national insurance, there really shouldn't be any difference in geographical distribution. Moving on, we're going to do the same pie chart on smokers. So you'll see that the majority of people don't smoke. Roughly every 1 in 5 people would smoke, which is good. And then we want to run the BMI distribution over here to see how our BMI is distributed in our population. And I have to say, it's not bad. It kind of looks like normal to me, a little bit, like it will never be perfect. But you have sort of your median around 30, and then you have quite a few obese people, and you have quite a few normal BMIs. We can also run some summaries with using the sort of selection and printing functions. I'm not going to go through this in detail. Essentially, you can say, hey, we have print something like this. We have this many smokers and non-smokers. But for the purposes of your analysis, I think this is a more important chart. So the question is, how come the pie chart had an X and Y axis? So it's because of it was coded that way. You see it has plot Y label frequency. Honestly, I don't think it's needed. It was probably the legacy from the previous chart over here. So you probably don't need it. Good point. Then it gets more interesting, right? So what we're trying essentially to do is we're trying to figure out what categories within our data have the most correlation with charges. And you can do that by running distribution charts of different columns against your charges category. For example, let's run this particular histogram. So what this histogram does is it gives us the frequency, the number of people by smoking condition, and shows us how they're distributed across charges. So who can tell me immediately what jumps out at you? What can you tell from this chart alone? Feel free to write in the chat. Skewed to the left. Yeah, so there are more people who have lower charges, sure. Bingo, Anthony, and Drew. So smokers pay a lot more. Correct, exactly. So you can see that almost all smokers have much higher charges than non-smokers, even though there are generally more non-smokers, right? So that's important. You can also layer that with a scatter plot scatter plot chart where we plot cost of treatment for smokers and non-smokers of different age. Again, you see that even though there is some correlation with age, of course, as your age goes up, your charges also go up. But look at red versus green, right? Where yes, if you're a non-smoker, as you age, your charges go up, but nowhere near the charges for smokers, right? So if you're a smoker, even if you're young, your charges are significantly higher. Who can quickly tell me here in the middle, I have sort of people all over the place. I have non-smokers who pay a lot. I have smokers who pay a lot. What would you say about the non-smokers here? Like, why are they higher? Why are some non-smokers here age? Well, you have age here, right? So BMI. Yes, David, you're right. So so exactly. We remember we only plotted smoking, age, and charges here. We'd never, there is nothing about BMI here. So what happens here, probably these non-smokers are obese. And yeah, so they may have pre other conditions, but they're not in the data, right? So we will never know. But what we do know is their BMI. Where I'm trying to go with this is, so you can run other charts here. You can run other distribution charts. Sorry, I have to run this first, and then this one. But my point is, um, and you see here also that there's like charges go up as you with the BMI, for the obese people. Here, you still have quite a few obese people, but they're probably younger. But the point I'm trying to make here is that you can spot some correlations even with the charts like this. But you see how it gets more and more complicated, right? So here we're showing BMI versus charges, and we already have all kinds of colors, but we don't have smoking status. Here we have smoking status, but we don't have BMI. And as you get more multidimensional, it becomes harder and harder to plot that on a chart. And where I'm going with this is this is where machine learning becomes as its best. So it really plays a big role, because what machine learning can do is, even when you have lots and lots and lots of variables, it can spot the correlations within those variables as they play together and have an effect on your dependent variable. And this is the power of machine learning. You don't have to spot these correlations. You can run them all simultaneously and see their overall impact on your charges. So what we're going to do next is we're going to split the data. Why do we need to split the data? Remember, we talked about the ground truth, and in supervised machine learning, the ground truth is usually what you're training on. So you're essentially splitting your data 30/70 or 20/80, and you train your data on the majority of your data set. So let's pick 80%. So you split your data 80/20, you train the data on the 80%. And then what you do with the 20% is you withhold the charges, and then you say, given these um, parameters of the customer, what will be their charge? And the model is trying to predict that. And then what you do is you compare that outcome of the model to the real charge that those 20% had. And that's what gives you confidence in the data. So in your test set, if you predict that the charge is, I don't know, $5,000, but the real charge is 5,200, that means you did pretty well with your prediction. But if you predicted 5,000 and the real charge is 10,000, then you know that you have a problem with your data. Okay. So that's what we're going to do. We're going to split our data. So we're going to use this function, train test split. And we're going to create our split. So in our split, we're going to do, I think it's 80%, if I'm not mistaken. Yes, 80%. So 80% is going to be our training, and then 20% is going to be our test data set. And what we need to do the next is feature engineering. I'm not going to run through this because we won't have time, but what I want you to know is there are two functions that we will use on our training and test data. The fit transform is the function that we use to train, and transform is the function that we use for sorry about that, for the test data. The reason you do that is to prevent what is known as data leakage. Essentially, what it does is it tries to prevent overfitting. So you fit transform only on your training set so that you have that ground truth, and transform you only use on test data because you don't want to you don't want the data, the ground truth from the test data set to become part of your training. That defeats the whole point, right? You want to withhold the charges from the test data set and then compare your prediction to the real ground truth. So this is what we're going to do. And we're also going to use the label encoder. So label encoder is used, remember I said that sometimes for machine learning models, you should change your categorical variables to numerical values. So in this case, that's what we're going to do. We're going to turn sex, for example, into zeros and ones, smokers into zeros and ones, and regions into 0, 1 to 3. Again, it's better for processing of the models. And then we use fit transform. And we also we use the transform on the test. The one thing that I missed to say was when you run these distribution charts, one of the values that you have from them is it gives you some level of understanding of what could be the variables that impact your charges. So sometimes maybe you don't need every single variable to include in your model. Maybe you can drop some of them. But I typically recommend that unless you have thousands of variables, that you try to kind of test as many of them as possible, because sometimes you just don't really know what's going to come out of your machine learning model, and withholding data is not always a great approach. So I'm going to run the label encoder, and now I'm ready for my modeling. So in the modeling step, we need to first define the model, fit the model to train the data, and then check the errors. So we're going to run the linear regression from the scikit-learn, and we're going to also check the fit. So here's where we define our model. So we're going to import linear regression and then just run the linear regression against our model. Remember what I said before, literally just calling on the linear regression, creating creating the function called model, and then running the model fit on our X train and Y train split data sets is enough to get your results of the model, right? So it's beautiful in the sense that you don't have to code the regression itself. All you need to do is split your data set and just call on the linear regression. Our model is trained. And what we now want to do is we want to check the accuracy of the model. We're going to do it with the function score. and are using our test, y-test, and x-test and y-test data sets. So that 20% split that we 20% splitting data set will this is where we're going to compare the predicted values with the real values in the test data set. And we see that our score is 0.8. So that means that we're 80% confident in our model. Honestly, it's very good, right? And remember, we're not trying to save lives here. We're just trying to predict charges. 80% is a pretty good first kind of pass. Without anything, we haven't done anything to the data. We don't have that much data. And with that, we have 80% accuracy. I would say it's a pretty good result. And the final step here is to actually run the new prediction. So in our case here, we can put in any combination of our variables. So in this case, it would be age, sex, BMI, children, smoker, and region. You can pick whatever you want. So in this case, we picked 50 years old person, male, who has BMI of 29, has one child, is a smoker, and is in the Southeast region. That's what this means, right? So you can pick whatever you want, but this was the example, what the example picked. So we're going to prepare our new data. We're going to run prediction against our new data, and then we're going to print our predicted values. So right here, we have predicted charges, and our predicted charges for this individual is $34,712. So you see the tangible outcome of this model. We're able, with 80% of accuracy, say that that if the male is 50 years old with all these characteristics, the charge that the insurance will have for this person will be $34,700. Okay. We can also run the feature importance. So trying to understand which features or which columns in the model have the biggest impact on charges. And no surprise there, smoker is the biggest predictor of the charges. And just like that, we have our not only model done, but also an ability to predict any new arriving customer, what their charges will be. Yeah, exactly. Making a person a non-smoker cuts the price down to a third. Exactly. Drew asked a good question. When you split the data, does it split randomly? Yes, I believe so. Okay. I know we breezed through it, but so I hope you focused on the big picture, right? So just sort of big buckets. If you want to get closer into the code, this particular notebook is with you, so feel free to do that. If you have questions, feel free to reach out to your TAs after this class. You can also ask me questions. But what we're gonna do is I'm gonna give maybe a minute for you to write your questions. And if we don't have any questions, we'll take a 10-minute break, and then we will be back for the next two case studies. Okay. All right, let's take a 10-minute break. We'll be back like 5 minutes after the hour, and we will continue.
Okay, thanks, Tatiana. We'll pause. Cool.
Welcome back, everyone. This is not my screen. Let me share my screen, and we'll continue. All right, let's go dive right back in, and we will talk about classification models. Again, I will start with the theory and then we will move into an example. In this time, so remember, we have about 50 minutes left and two case study to go through. Remember what I said at the beginning about the first study. Even though it felt like we breezed through it, we still spent almost an hour on the first one, right? So the second one, I will go faster. Not and I'm not gonna go faster as in I'm gonna talk faster or skip things. It's just some of the building blocks of the second case study are exactly the same as the first one. So I'm just going to name them, run them, show the results to you, but I'm not going to talk about how to do them or why we're doing them, right? Because we covered them already. The new stuff within the classification models, I will spend more time on. Okay. All right, so what are the classification models? The classification is basically like sorting objects into different groups. So imagine you have a bunch of toys that you're trying to organize. And let's say you decide to put all the dolls into one group, stuffed animals into another one, and maybe another categories for Lego, for example. And so what the way classification models work is exactly the same way. You want to categorize your data and based on its characteristics, predict what category or what group that object is going to belong to. So let's stay with our toys example, right? Uh, let's say you say, hey, I'm looking at all my toys within the doll category, right? And I say, you know what? If the toy looks like a person, if they have a head, two arms and two legs, and the hair, with a high degree of confidence, I'm going to say it's a doll. But if my toy is squishy and is made of fabric and is not doesn't look like a human being, then it's most likely a stuffed animal. And then for the third category is if it's plastic and it's mostly a rectangular shape, then and it doesn't look like a human or an animal, then it's most likely a Lego block, right? So you can see that I have attributes of a toy, but based on these attributes, I'm trying to predict which category that toy belongs to. So how do they work? Let's look at the more real world examples. Let's say you have a spam filtering software on your computer that tries to place your email into spam versus non-spam. The classification model is most likely running behind that spam filter because you have a lot of historical data on emails that other people categorized as spam. And so you can gather a lot of data on emails that are categorized as spam and not spam. And then you know a lot of things about these emails. So for example, you know that they have titles of those emails are in caps lock, or let's say they have words like save now or click here or expire, right? So maybe there's certain language within the email. Maybe there's a lot of like I said, caps lock, or maybe there's a lot of imaging in the email that suggests that it's a spam. That's because the classification model that's built in the background predicted that these types of characteristics of an email make it very likely to be a spam. And then if those characteristics are not present, then that email probably is not placed into a spam folder. What are the different types of classification models? The most common one is called logistic regression. Logistic regression is one of the most common ones. Usually, it's the model that operates with two categories. So let's say spam, non-spam, right? Or dog, not dog, Lego or not Lego, right? So those are the types of use cases for which logistic regression will be used. When you have multiple categories, you can use something like decision trees, which I'll talk about in a second. You can use something that's called multinomial regression models, and so on. But the logistic regression is the more common one. And the way that it works, or the function of logistic regression works, is as follows. So you have sort of the sigmoid function, right? And then the probability goes from 0 to 1. So it's either non-spam or spam. And then you have your observations kind of like everywhere. And then you have to pick a threshold. And most often the threshold is 0.5, so 50%. Basically, you say you kind of cut across here, and then you say all the observations that lie over here are going to be spam, and then below this line is going to be non-spam. Yeah, so if your characteristics of an email are such that your sigmoid function is over 0.5, then it's a spam, and if it's lower, then it's 0, non-spam. And then the second one is called decision tree. So decision tree works a little bit differently. The way the decision tree works is it tries to identify a factor for your email that differentiates it into different groups. So, for example, let's take an example of caps lock, right? The header of your email is in caps lock. What decision tree tries to do is it looks at that first factor. It looks at caps lock and it says, hey, is this email written in caps lock? Yes or no? If it's a yes, then go next. Go to the next branch. If it's a no, then go to this branch. And then in here, in these branches, let's say it says the email uses a lot of images over here. Does the email use a lot of images? Yes. So then most likely a spam. No, maybe not a spam. And when I say spam, not spam, usually these are the probabilities here. So is it less than 0.5 or is it more than 0.5? And the same is here. Images, non-image, no images. So the fundamental difference between decision trees and the logistic regression is that in logistic regression, you look at all these different characteristics of an email at the same time. And then you get that one probability at the end. Whereas in decision trees, you start with one characteristic and then you split your data based on that. And then you go to the next characteristic and the next one and the next one. And that creates your decision tree splits, right? So the end is the same, but the how you get there is slightly different. There are two things to know about classification models, accuracy and confusion matrix. So accuracy basically tells you how confident you are that your model is correct. And usually it's in percentages, right? Like 80% confident, 30% confident, and so on. Confusion matrix is essentially a table that tells you how many true positives and true negatives and false positives and false negatives you got. So what is the confusion matrix? Let's look at it more closely. So you have true positives and true negatives. What that means is that the model predicted that the email is a spam, and it is really a spam. Right? Remember this whole training set and test set? So basically, you train your model, you got your probability, and then you take your test set, you try to predict, based on the model, you're trying to predict the spam likelihood, and then you look at the actual data and you compare. Was it true or was it not true? So if you predicted spam and it's a spam, it's a true positive. If you predicted non-spam and it is a non-spam, it's a true negative. But then, of course, you have others. So sometimes you predict you predict that it's spam and it's not spam. And sometimes you predict non-spam and it is a spam. So why is this important? Like, why do we care about this confusion matrix? And it's actually one of the cornerstones of the classification models. That's because you have to figure out something that's called precision and recall. What are those things? Precision essentially tells you of all predictions, all the spams that all the emails that you've characterized as spams, how many are really spams, right? So I don't know, you have 1,000 emails, you decided that, 50 of them, 500 of them are spams, and 400 of them are truly spams. That's your precision, right? So your precision is 400 over 500. Uh, that so that is one metric that is very important. The second metric that's important is recall. So recall means that of actual positive cases that you've identified. So the correctly predicted or the predicted cases that you've identified, how many are negative, were incorrectly classified as positive, so they're negative. That is recall. The reason why it's important to differentiate between precision and recall is because depending on what your goal is, you may want to decide for a higher precision or a higher recall. Let's take an example of spam, right? Email spam. So what is more important, to falsely predict spam, or not catch enough spams? What do you think? What do you think is more important? That you didn't identify enough spam emails, or that you identified too many spam emails? Too many. Yeah, too many. Exactly. So if you let's look at an email of a regular person, right? I get emails every day, and then let's say I'm just going to exaggerate, like all of them become spam. I'm going to miss very important information. Whereas, let's say the person has cancer, and the person has cancer, and you have to choose whether the patients who you have, you predicted too many cancer cases and that person still made it. But there are some other people who didn't have cancer, but they got classified as cancer, or that you missed cancer, that you haven't identified enough cancer cases, but the ones that you did identify were correct. So which one is more important for cancer? To identify too many cancer patients, or not enough? Not enough. Exactly. So so it's a scare. It's a medical scare. If you tell someone, hey, you might have cancer, it's crazy. But it's much worse to not tell someone who have a cancer that they have a cancer, and then later find out they have a cancer, right? So hopefully it gives you an idea, right? So when you optimize precision, that's your spam example. That it's you want to, having false negative is not a big deal. But you really want to make sure that you have true positives optimized. Whereas in recall, having a lot of false negatives is a problem. Right? Okay, so I think this is it. Yeah, this is it for the theory. And let's jump right into the case study. Okay, so learning objective, we are working for a loan. We're working for a bank, actually, and the bank is trying to figure out who to give the loan to, approve or disapprove. And they have all this data on the loan takers. So gender, married, number of dependents, education, whether they're self-employed, income, co-applicant income, loan amount, the term of loan, credit history, meaning that their credit history meets the guidelines, property area, and loan status. So loan status is what we're going to predict, whether their loan will be approved or not. And our goal is to do just that, right? To figure out whether the loan is approved or not. So we're gonna import all these libraries. like I said before, there are the differences. Logistic regression is going to be here. We're going to use this as opposed to linear regression. Most of the stuff is the same. We're going to load the data. Same thing. You see the headers. You see all these different variables. You look at the shape. This is what I said. I'm going to skip over some of the stuff because they're exactly the same. We're going to look at the missing values. You see there is a lot more missing values here, so we're going to try and replace them right here. So you see how many, some of them have a lot of missing values. Then we're going to do describe function. So in describe function, you have all these different characteristics of your numerical data and also your categorical data right here. So you see there is a different way of looking at the like the values of the categories. So for example, in the property area, if you run the property function and then you count the number of values for it, you see that there is semi-urban, urban, rural areas, and you see the count for each one of them. The same for dependence. So for example, here, dependence is, you'll find that it's not an actual numerical function or variable because you have this 3 plus, so it's not a continuous variable, and therefore you have those categories. We're going to clean the data the same way. We accept, instead of dropping missing values, we're going to fill them, and we will fill them with, for categorical variables, we'll fill them with a mode. It's the most commonly used value. And for the numerical variable, we will replace it with a mean. So married, dependent, self-employed, credit history, and gender will replace with mode, missing values, and the loan amount we will replace with mean. Okay, and then we will run again to make sure that we don't have missing values. The only one where we do have missing values is loan amount term, but that's okay. Only 14 cases. And then what we also want to do is we want to replace the number of dependents. Instead of 3 plus, we just want to replace it with 3 so that the model treats that as a numeric variable. Moving into visualization, again, I am moving fast just because we've done this already. We're going to run the histograms. So you see this is the histogram of the loan amount. You see the majority of the loans are between $100 and $200 with some of the outliers here. The same thing gonna go for application income. It's monthly income. You see that the majority of people's monthly income is under $10,000 with some of the outliers. Co-application income is about half of that, so under $5,000 monthly. We can run the gender charts. So you see that there is a female and male, and then this by the status of the loan. So you see that even though more men tend to take out loan than women, if you look at the proportion of approved versus non-approved loans, actually it looks like women are slightly more likely to get their loans approved compared to male. And again, you're just looking at by comparing these two charts, these two bars. Right? Same goes for credit history. So you see that having a credit history is definitely puts you at higher odds of getting it approved. Then we have dependents, so number of dependents. It looks like, again, if you compare the charts to each other, you see that not having dependents increases your likelihood of loan approval. The education, so being a graduate seems like you're a higher odds of being approved if you're a graduate versus if you're non-graduate. Being married puts you at higher odds of getting your loan approved. Property area, it seems like urban, semi-urban puts you at a higher chance of getting loan approved than either urban or rural. Self-employed doesn't seem to make a difference. The difference between these two is slightly, maybe more or less the same as these two. So self-employed or non-self-employed probably doesn't make a dent. And that's it. So you see that just looking at the bar charts, we're trying to figure out how all these different variables affect our loan status approval odds, right? But again, this is not a scientific approach. This is quite manual. And what we're going to do is we're going to use a logistic regression to tell us what are those factors of approval. Again, we're going to split our data into training and test. We'll do feature engineering with label encoders, exactly the same thing as we did before. We're going to change our married education property area into 0, 1 or 0, 1 to 3, 4, and so on. Convert dependence into an actual numeric field. And we're now ready for modeling. So in the model, we're going to use logistic regression, right? Logistic regression. And we're going to apply logistic regression to our X train and Y train, and then use the perform or transform function on our test function. So remember model logistic regression, the same thing, model fit X train, Y train, model trained. Did I run this? Hopefully this. It's going fast, so I probably missed a couple steps. Interesting. Let me run this again. So what happened probably is I missed a step. And now I have to trace back. So this I don't need to do. This I don't need to do. Dropped variables, data splitting. This is important. This is important. Let's try. All right. Sorry about that. I think I didn't run every code. So we're back on track. So hopefully you got the same thing. So it has the same model trained over here in line 37. So what we did here, we defined our regression model, we trained our data, and now we will look at the model score. Remember, I said that the score, the accuracy will be a score that predicts how accurate our model is, how confident we are in its prediction. So it's going to be 0.78, which is very high. Again, pretty good result. And then we're also going to run the precision and recall. So you see precision is 76 and recall is 98. Because we're looking at the loan amounts, right? So the loan status probability. What do you think is better here, higher precision or higher recall? Is it better to get too many approved or not enough approved? Oh, we have split opinions. Too many. Too many, not enough. So we have a split in opinions. So you know why? Because it depends. It depends what your strategy is, right? So sometimes let's say you want to, you want to kind of, let's say you're a new bank and you're trying to get a lot of new customers. Then maybe it's better to pre-approve most people and then reject some down the line. Then if you are, let's say, an established bank, then maybe you have so many customers that you can't manually review every one of them. And so you would want to approve people automatically, if only if you're too super sure about them. If you're not sure, you're just going to punt them into the manual review process, which is, by the way, in the US, the majority of banks do that, right? Like you would go into something like a Macy's and they say, hey, do you have a loyalty card with us? Would you like to apply for one? And then you notice that they tell you basically right away. You put in your information and they tell you right away if you're approved or not. That's probably the bank that tries to maximize recall. So this one, because what they're saying is that we want to only approve those that are slam dunks, and then people were not sure, false negatives, potential false negatives. We want to minimize them, and we're going to punt questionable people over to manual review. But if the bank is small and just starting out, then for them precision is going to be more important. So this is your confusion matrix. You see we have higher recall. So um, you have um, you have very few false negatives, but you have quite a few false positives, which is basically consistent with our results here. That's it. So just keep in mind that so what you need to do is you need to make sure you don't skip the steps. I think I skipped a few. So the models didn't run. So when you run it by yourself, just make sure you run through all the codes. But the main thing is, so before we ran linear regression, here we're running logistic regression. You're modeling on the training set, and then you're running your score against your test set to get the accuracy, and then you get the recall and precision. And depending on what your goal is, you try to maximize one or the other. It's almost impossible to get both of them at the same level. Usually you have to do a trade-off. Okay, so that was the classification model. I'm going to go ahead and dive right into our unsupervised machine learning. We have about 25 minutes left. So and again, don't focus on the code, just look at the big picture, okay? So in the unsupervised world, remember, it's not about training the data. There's no ground truth. What you're trying to do is create associations. And in association analysis, you're basically trying to say, um, you're trying to group things together that are more likely to appear together. So, for example, the most common use case is the supermarket buys or purchases. People who buy milk also buy cookies. Peanut butter, jelly, and bread are often bought together, and so on. This type of analysis is called association analysis. Association analysis essentially looks at pairings or sometimes combination of things that happen or appear often, and then it tries to associate them with each other. How does it work? You have in the association analysis, there are different algorithms, and one of them that is most common is called a priori. So a priori analysis essentially helps you create that market basket associations. There are different terms that we will cover today in association analysis. The three most important ones are support. Support means popularity. So support measures how popular a combination is. Um, so for example, if you have, of all your purchases, if bread and butter appears, let's say 5 times out of 10 purchases, your support is 0.5. Lift is a surprise factor. So surprise factor meaning that there is a combination that appears, it appears, but it's not common. It's not something you would expect to see. For example, I don't know, an example could be diapers and beer, right? So it's it's a surprising combination, but it appears enough times for you to pay attention to it. And then the confidence. So the confidence says, how sure are you that these combinations appear often, right? And that again is sort of your measurement of the confidence in the model that you build. There are different analysis applications. We will only focus on the market basket analysis today, but there's text mining. So for example, if you look at the large language models and generative AI, they take their roots in text mining. And text mining is nothing but trying to figure out which words appear closely together. Web analysis, so trying to understand the patterns in the browsing history of people, and then scientific research to understand, the interactions between genes and proteins and so on. Let's dive into our exercise. So the learning objective here is to identify associations within your supermarket purchase history. We again will import some libraries. The main library that we will import is called ML Extend. So it stands for Machine Learning Extensions, and it includes market basket analysis that we will be running today. Then your familiar pre-processing, the encoders, the frequent patterns will allow us to find the patterns. A priori is that algorithm within market basket that we will use. And then association rules is another function that generates association rules for us. So we'll go ahead and import them and read the head of the data. So we're loading this data set, basket optimization. And you see that this is what the data looks like. So the way to read this data is it's literally lists of purchases. So the first purchase has shrimp, almonds, avocados, vegetables, and so on, up to 20. The next one has burgers, meatballs, and eggs. And you see the rest is NaN. NaN stands for not a number. Now, the reason why you have a lot of what looks like missing values is because everyone's purchase list is different. Some people buy 5 items, some people buy 55 items, right? So the missing values are not missing in the sense that there should be a value there. It's intentional. So in this case, the maximum is 20. So you know that there will be no list with more than 20 items. But then you also see that there are lists that are much smaller than that. Let's check the shape of the data again. So we'll run the data. We'll see that there are 7,500 rows and 20 columns. Let's check the nulls. So when we run the nulls, you'll see that there are no null values. And that's, again, intentional because NaN is not treated by Python as null. It's treated as a value. Okay. If it was missing, let's say truly no value there, then it would treat it as missing. So we have no missing value from that standpoint. So the first thing we need to do is transform our data into a list of lists. What do I mean by that? So this data format is actually not useful for Python. It doesn't really know what to do with it. What we need to give Python is something that looks like this. You see the brackets, and in the brackets, you just have lists. And the reason it's called list of lists is because you start with a list and then you add small lists into each one. So this is the first list. Then there is a second list, a third list, and so on. This is a more palatable format but still a temporary format for Python to read. We will have to transform this list as well. But for now, this is our first step, is to transform our original data set. Then we need to do another transformation into a data frame. So we take the list of lists, and what we need to do also is we need to create, kind of like flip the original table on its head and turn each product into a column, then turn each list into a row, and then just use encoder to tell Python whether that product was purchased or not, right? So for example, in the first list, was asparagus included? No. Almonds, yes. Juice, yes. Asparagus, no. Again, asparagus. Avocado, yes. Baby foods, no. Bacon, no. And so on, right? So this is another interim format that we need to use to get to the modeling stage. So I'm going to run this, the transaction encoder to encode false and trues. And then I'm going to use the fit transform to create an array of our data sets. And then I will also drop the NANs. So in case I have a column called NAN, I want to drop it. Okay. And now we are on to the modeling. So remember, there is no modeling per se here. There's no ground truth. There's no predictions here. We're just trying to find associations. So we'll be using the a priori algorithm for our baskets data frame to find the products that are purchased together more often than others. So we're going to specify the min support as 0.004. What that means is we want to set the threshold of the support to 0.4%, meaning that the transactions that happen less than 0.4% in all the lists, we don't want them, right? We want to separate them. The reason we put some level of support threshold here is because otherwise we'll end up with so many combinations, it's not going to be practical to look at them. 0.4% is reasonable, right? Like it's not super high, but it's not low. And so we're going to run this analysis. And you see the output here. So the output essentially tells you for each item set, remember, item set is not always an item combination. Sometimes it's an item by itself. And the support tells us what percent of the time this item set is purchased together. So almonds with nothing else are purchased 0.2% of the time, or maybe 2% of the time. I think it's 2% of the time. Juice, 0.8% of the time. Asparagus, 0.4% of the time, and so on. But as you get to the combinations, like for example, this combination is purchased 0.4% of the time. And so that's why we put in the threshold, because we want to make sure that there's no combination that appears like 0.00005% of the time, because maybe we don't care about that. But this is by itself already very useful because you see the item sets and then you see how often they appear in your basket. The next is association rules. So in association rules, we're going to look for the basically the both support and the lift factor. And we're also going to introduce the thresholds here. So let's run the association rules and look at the output. So before we do that, I'll introduce the antecedents and consequence. So antecedents are the items that are purchased sort of like if you look at like almonds, like bread and butter, for example, antecedent is the bread and consequent is the butter. And that direction matters because, for example, you may find that bread and butter is purchased more often than butter and bread in that order. So it's always very important to understand who in that pair, who is the antecedent and who is the consequent. So let me give you an example. Let's take burgers and almonds. So burgers and almonds, their support is 0.08. So what is it, like 8.7%. So 8.7% of the time they appear together in that order. But if you flip that and if you say, what is the percent of the time almonds and burgers appear together, the support becomes 0.02. So you see that the combination of burgers and almonds is in that order, is purchased a lot more often than the um, almonds and burgers. Okay. And then the confidence, so you see the support, overall support would be the same, right? And the confidence would also be different. So, and then you do it for each combination, chocolate and almonds, almonds and chocolate, and so on. In this case, how do you know which came first? So if you do online shopping, it's easy, right? So you know which one you clicked on first. In offline purchases is harder. Usually, the way you'd have to make assumptions, but the way you would assume that is by how people move in the supermarket. So, for example, if you're like, let's say your bread is positioned before your like aisle with your like different butters, then you would assume the bread was purchased before. But then, of course, the reverse would be harder to figure out because how would you know that the person, how would you know that the almond butter or the butter was purchased before bread if the bread was positioned before the butter? So, and that could also be the bias, the introduction of the bias, because maybe you assuming that the bread was purchased before, but the reality was it was purchased after, but the person went back into the supermarket. So it's not easy. In offline purchases, is in online, it's quite easy, right? That's why when you buy something online, you'll notice that, let's say you buy, I don't know, you buy bread, right? And then at the bottom, you'll see that frequently purchased items, and you'll see butter there because you purchased bread. Um, so the rules, so of course, sometimes, so here you have a lot of different combinations. Let's say you want to figure out the top 3 combinations that have the highest lift and the highest confidence. So confidence is essentially how good is your model, right? And the lift is that surprise factor. Like, what are the items that are purchased, not commonly usually purchased together, but still appear quite often in your basket? And so here, when I run these rules, so I said that my lift has to be more than 2 and my confidence has to be more than 6, so 60% confident. And you see that I get these 3 combinations. The antecedent is soup and frozen vegetables, and consequent is mineral water. And so you see that this is a surprising combination. It's not common, but it's common enough in this particular list. The same with soup, pancakes, and mineral water, and tomato, olive oil, and spaghetti. So someone probably is making the spaghetti from scratch. No spaghetti, sorry, the sauce from scratch. Okay, so the this would be the more common or common but not obvious combinations that you would select based on these rules. Now, of course, you can relax these rules. If I add, let's say I change it to 1 and confidence still, 0.6. oh, still I have 3, right? So the point here is that you can always change the rules, and then that way you can see what your output, how your output will change. All right. Any questions? This is more digestible than supervised. Yeah, I would agree. I mean, part of it is that you don't have to train, right? All you do is essentially, so up to here, all you do is transform your data. And then the only real analysis starts over here, where you just look at your commonly purchased items, and then this is your output. So this from here, it's really the place where you start doing any kind of modeling. Whereas in supervised, you have to do the splitting, you have to do the train, then the test, and you have to run the scores and so on. Any other questions? While you're typing, so remember that when you go back, I would try to, first of all, run these codes, right? So just try to run them. And again, don't try to kind of analyze them yet, just run them and get comfortable. And then what I would suggest you do is you kind of like look at the blocks of code. So don't look at every single line. Just focus on the block. So for example, here all you do is importing, right? So just look at the block and say, okay, I see import, 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 right? I'm just importing, right? And then leave it at that. Leave it at that. Then go here and say, here I'm loading the data and I'm getting the headers. Okay, this is loading, this is getting the headers. Okay, here I'm just getting the shape of the data. I'm using shape, rows, columns, and printing. Okay, I got this, right? Then you go in and then you go kind of like on and on like this, right? This allows you to sort of peel the onion and get to high level picture to a lower level code. If you try to go line by line from the very beginning, you'll get overwhelmed, right? You'll be like, DF, what, where, why was I using it, right? And then that becomes sort of like overwhelming for you. Whereas if you look at the code, let's say 10 times, but you look at it from different angles, you familiarize yourself with it, and you would have seen, by the time you get to line by line analysis of the code, you would have seen the code like 10 times, and it becomes less daunting. When the data is large, it's easier to use Python to clean the data. Um, to clean the data, Python, it's fast. I don't know if it's the fastest. You can clean data with, like, let's say SQL, with very large amounts of data. Now, what I would say is that Python is the most versatile language. So Python is used for cleaning, transforming, loading, machine learning, visualization, everything under the sun. Whereas maybe some other languages are more narrow. Like SQL, for example, doesn't do machine learning or visualizations. What's the difference between having not a number and then getting rid of them and having nulls? If you do that, then Python will think that you have a lot of null values. It may not be a problem in and of itself as long as you remember to transform the data set. Where it might become a problem is if you're running a supervised model and it's NaN and you don't realize it's NaN and you think that there are no null values, then you might get in trouble. But then I would recommend that you look at the unique values of each category. If you run that code, then you'll see that NaN will show up as a category itself. All right. If there are no more questions, I'll pass it back over to